7/10 of the Earth's surface is covered by water, endlessly moving, endlessly wearing away the land. The countless streams and rivers also wear away the land as they move, carrying tiny fragments downstream into the sea. If we took a sample of seawater, it would show us some of this material. Yet even after the particles have settled, a single taste tells us that there is salt in the water. The salt, which we know was once solid material, is now invisible, finer than the finest sand or clays. We'll take a little of this water and evaporate it under a heat lamp. With the camera speeding the action, we see crystals appear. Crystals of soluble minerals that were dissolved in the water. Minerals that were in solution in the sea. The sea, then, is really a tremendous solution. What kinds of solutions are there, and how do we use them? To have a working knowledge of solutions, we must first learn some definitions. We say that a solution has two components. The sugar, in this case, is the solute, the substance we will dissolve. The water is the solvent, that is, the substance in which the solute is dissolved. There are three important characteristics that will help us identify a solution. The first characteristic is that solute particles become molecular or ionic in size. Second, solute and solvent particles become and remain uniformly dispersed. Dispersal is homogeneous. A third characteristic is different concentrations of a solution are possible. Unlike a compound, the ratio of constituents may vary. Let's examine the first point. Solute particles become molecular or ionic in size. Into a container suspended in water, we introduce soluble crystals of potassium permanganate. Almost immediately, the crystals begin to dissolve, becoming ionic in size. In time, through the activity of the water molecules, the ions are dispersed throughout the solution, coloring it uniformly. In a solution, solute particles, being molecular or ionic in size, come through the finest types of filters and even through semi-permeable membranes. The portion of solution we filtered, called the filtrate, is the same as the original solution. If we divide this quantity of our solution into 4 exactly equal parts, each part contains exactly 1/4 of the solute we originally dissolved and 1/4 of the solvent used. If we had taken the same solution and divided it into 10 equal portions, each portion would have contained exactly 1/10 of both solute and solvent. So, in a solution, solute and solvent particles become and remain uniformly dispersed. A third characteristic of a solution is that it may vary in concentration by varying the proportion of solute to solvent. Here we've added a few crystals of a salt, copper sulfate, to water, making a very dilute solution. If we add a large amount of solute, we say we have a concentrated solution after it has dissolved. And if we keep adding solute until no more will dissolve, we have a saturated solution. A given solvent does not necessarily dissolve all substances equally. Solubility varies with different solutes. Carbon, for example, apparently does not dissolve in water. Careful analysis would show that about 1 part of carbon dissolves in 10,000 parts of water. When solubility is so slight, we may say that carbon is insoluble in water. If we use calcium hydroxide, about 2/10 of a gram dissolves in 100 grams of water, about 1 part in 500. At this ratio, we say a substance is slightly soluble. In this example, we dissolve 12 grams of sodium sulfate in 100 grams of water, roughly a ratio of 1 to 10. Substances which dissolve in ratios of 1 to 10 up to 1 to 30 we call soluble. In this final example, 110 grams of sodium hydroxide dissolved in 100 grams of water. Actually, we have used more solute than solvent. In such a case, we call the substance very soluble. Solubility also varies with the solvent. Here we have a solute, copper sulfate, and 3 solvents, oil, petroleum ether, and water. For example, the salt, copper sulfate, is soluble in water, as we saw earlier. Now, instead of water, we'll try a different solvent, oil. Copper sulfate is insoluble in oil. In our next example, using water again as our solvent, we will try oil as the solute. We see that oil is insoluble in water. Let's try oil with a different solvent, petroleum ether. Oil is soluble in the ether. The chemical factors influencing solubility are complex, but we can remember one general rule. Usually, like dissolves like. That is, an organic substance, like oil, is soluble in an organic substance, petroleum ether. Also, inorganic substances, such as our salt, are more likely to dissolve in inorganic solvents, such as water. Again, in general, like dissolves like. Physical factors also influence solubility. One factor is the particle size of the solute. Here are 2 large crystals of the same solute. We'll pulverize one crystal. Using equal amounts of our solvent, water, we place a whole crystal into one beaker and the finely ground crystal into the other. We can see that generally, the finer the material, the more rapidly it dissolves. Agitation is a second physical factor that increases speed of solution. Shaking or stirring a solution makes the solute dissolve faster. Other physical factors influence the degree of solubility. Generally, heating a solution will increase the degree of solubility. Here we have a saturated solution of copper sulfate at room temperature. After heating for a time, not only has the excess solute dissolved, but we can dissolve even more solute than would have dissolved at lower temperatures. We get similar results with most solutions. Heating generally increases the degree of solubility of solids in liquids, of liquids in liquids, and of solids in solids. Here we are preparing to heat a soft drink, which is a solution of a gas, carbon dioxide, in liquid. As the liquid is warmed by room temperature, bubbles of gas come out of solution. As we heat the solution, more bubbles of gas are driven off. The solubility is decreased. So, heating decreases the solubility of a gas in a liquid. Another physical factor, pressure, affects the degree of solubility of gases in liquids. This drink is bottled under pressure so that more carbon dioxide gas will dissolve in the liquid. Increased pressure increases solubility. We've considered mainly solutions of solids in liquids, such as a salt in water. We also saw a gas dissolved in a liquid to make a solution. There are other kinds of solutions possible. What about a gas dissolved in another gas? We can mix chlorine in the flask with bromine vapor, for example. As they mix, it would be hard to say which is solute and which is solvent, but the mixture fits the definition of a solution. Molecular-sized particles, uniformly dispersed. In proportions we can vary. Another kind of solution is one we saw before. Oil dissolved in petroleum ether is a solution of one liquid in another liquid. Knowledge about solutions can be useful in many ways. That solutions of an acid and a base, when mixed, can neutralize each other. The exact point at which neutralization takes place depends on the concentration of each solution. If the concentration of one solution is known, the other can be determined by a procedure called titration. With the aid of this accurate equipment, an analytical balance, and a burette, we have prepared a normal solution of sodium hydroxide, a base. We define a normal solution as one which contains one equivalent weight of a substance per liter of solution. Our volumetric flask contains a 1 normal solution, exactly 40 grams of sodium hydroxide in exactly 1 liter of solution. 1 liter of this 1 normal base will neutralize 1 liter of 1 normal solution of any acid. We're going to use this fact to help determine what the concentration is of this solution of hydrochloric acid. First, we'll fill a volumetric flask with exactly 100 milliliters of our hydrochloric acid. We overfill, then use a pipette to bring the level down to exactly 100 milliliters. The measured volume of acid is put carefully into a flask. Now we'll add an indicator, methyl red. The indicator will change color when neutralization is completed, when all this acid has reacted with an equivalent amount of base. Into the burette, a calibrated tube used to measure milliliters and fractions of milliliters. We pour the normal solution of the base, sodium hydroxide. We overfill and then carefully withdraw some of the base. The reading is 1 1/10 milliliter, which we will note. We release our known or standard base solution of sodium hydroxide into our acid of unknown concentration. We complete the reaction cautiously, drop by drop. Now, the color changed indicates that the process of neutralization is complete. Now we read the differences in level to find how much base we had to add. Subtracting our original figure, 1 1/10, from 31 1/10, we know it took 30 milliliters of 1 normal base, or 30 milliequivalents. Then there must have been the same amount, that is, 30 milliequivalents of acid. Knowing the exact volume of acid we had, it is possible to calculate the concentration of the acid. In this case, the solution is 3/10 normal. This was only a simplified example of the process of titration, or reacting amounts of a solution of known concentration with a solution of unknown concentration. Titration is an important technique in a subject called quantitative analysis, which you may someday study. Titration is one of the many ways we put our knowledge of solutions to work. Another application of solutions is the use of a solution as a cleanser. A solution of carbon tetrachloride, for example, is a solvent that will dissolve grease and so remove it from the cloth. Everyday solutions include antifreeze in your car, perfumes of many kinds, and many common medicines. Sometimes we may want to separate one or more substances from several in solution. In organic chemistry, the process of distillation is often used to separate components of a solution. A second useful method of separating solutions is to crystallize out a solute from solution. By heating the solution in the dish, we can reduce the quantity of the solvent by evaporation. Here, with the camera speeding the action, we see the crystallized solute appearing. The process of crystallization is used in many ways. The table salt you use may have been crystallized from a salt solution. This metal, magnesium, was produced in this plant from magnesium salts, which were crystallized from seawater. Although solutions have been used for centuries, our knowledge in this area of science is still far from complete. There is room for continued study and experimentation to increase our understanding of solutions.